All right, we're just going to do some multiple choice practice here. So I've compiled a big ol' list of multiple choice questions about all things rotation. Only thing absent from this is angular momentum. So that's for later, but everything else, rolling without slipping, all that stuff is going on over here. So, first, a wheel of mass m and radius r rolls on a level surface without slipping. If the angular velocity of the wheel is omega, what is its linear momentum? Well, uh, we're asked to find a linear momentum, and linear momentum is P, which is equal to mv. So P equals mv. Well, that's not an answer choice. So I need to figure out how I can rewrite this in terms of one of the answer choices. And we're given the angular velocity of this. We're given that it's omega, and we also are given the magic words without slipping. So the fact that there's no slipping going on here means that the angular velocity and linear velocity are related by v equals omega r. So we can just replace the v down here with an omega r, and we get m times omega times r, and that is answer choice A. A turntable that is initially at rest is set in motion with a constant angular acceleration alpha. What is the angular velocity of the turntable after it has made one complete revolution? Okay, so notice we're given alpha. We're given that it's at rest initially, and we want to find its final angular velocity. So this is a kinematics situation. So we're given alpha, omega naught equals 0, and we're also given one revolution. So the trick for this is to realize that for one revolution, that's equal to 2 pi radians. So we can just apply the kinematics equation that omega squared at the end is equal to the initial omega squared plus 2 times alpha times delta theta. So omega squared is just going to be equal to 0 squared plus 2 times alpha times 2 pi. So omega is just going to be the square root of 4 pi alpha, which is C. So again, the trick for this, it is just kinematics, but you had to realize that one revolution is the same thing as displacing 2 pi radians. A disk is free to rotate about an axis perpendicular to the disk through its center. If the disk starts in rest and accelerates uniformly at a rate of 3 rads per second for 4 seconds, what is its angular displacement? So once again, we can just set up our little kinematics. So delta theta, omega naught, omega final, alpha, and t. Well, we don't know the angular displacement. That's what we want to find. We know that we start from rest. We're not given omega final. The angular acceleration is 3 radians per second squared, and the time is 4 seconds. So this means that we're going to use the kinematics equation that does not contain omega final, and that's just going to be our typical displacement time equation. So it's the 1/2 at squared equation, but for angular kinematics. So in this case, our angular acceleration is 3 rads per second squared. We're accelerating for 4 seconds, and we're starting at rest, so that term's 0. So this is just going to be 16 divided by 2 is 8. 8 times 3 is 24 radians. That's answer choice D. what is the ratio of angular velocities on a rotating body at a point half a radius away from its axis of rotation to a point 1 radius away? So just to draw a picture, what this is asking is what is the ratio of angular velocities on a rotating body for a point half a radius away. So that's something like this in blue versus 1 radius away, which would be this in purple. Well, we have to use the fact that the definition of a rotating body, well, everything in here is going to be rotating at the same rate. So actually, for a rotating body, omega is constant at all points. It's the linear velocity that changes because everything is sweeping out a circle at the same rate. That's what it means for this body to have angular velocity. Every point on this body is completing a revolution in the same amount of time. So it's actually just equal, which is c. So the omegas are equal. What's not the same is the linear velocities. So v at a point r is going to be equal to 2 times the v at a distance of r over 2. Because the r, you're traveling twice as far in the same amount of time. So the revolution time is the same, which is related to omega. A wheel of radius r and of negligible mass is mounted on a horizontal frictionless axle so that the wheel's in a vertical plane. Then we have 3 small masses placed on this, but the system's in static equilibrium. And we want to figure out what relationship these masses have with each other. So we're given that this is in static equilibrium, meaning that all the torques of these have to cancel out. So the easier torques to calculate is going to be the torque from the 2m and the torque from the m, because they are just linear. They're exactly perpendicular, so no trigonometry required. But then for this big M right here, we are going to have to figure out how that angle associates with that. Like that. So let's just kind of start. So we know that the actual magnitudes of the forces, so this is a 2mg, this is a little mg, and this is a mg. And then we just got to set the torques equal to each other. So we can see that the mg is attempting to rotate the wheel clockwise, whereas the other 2 torques are combining to try and rotate it counterclockwise. So what we need is the torque from the 2mg to equal the torque from the little mg plus the torque from the big mg. And for this one, we're going to utilize the idea of lever arm. So torque is equal to lever arm times the force. So for the 2mg, and again, the lever arm is just the shortest perpendicular distance between the point of rotation and the line of action of the force. So it's perpendicular for these masses directly on the axis. So for the 2mg, the torque is just going to be 2mg times r. And the same thing for the little mg, it's just going to be mg times r. Because the line of action is exactly perpendicular to the distance. Now we got to figure out what the lever arm is for the other mg force right here. So mg is really good to use the lever arm method for because mg is always a vertical force. So what the lever arm is for a gravitational torque is it's just asking what is the shortest horizontal distance between between the pivot point and the line of action of the force. So if this is r and this is 60, this point right here is r cosine 60 degrees. So the lever arm for our 60-degree angle one right here, it's just going to be the force is mg, but the lever arm is r cosine 60 degrees in this case. You could do just the theta between method and work that out as well. But here I like lever arm because I know it's just going to be a horizontal distance. So this just says that 2 big mgr is equal to little mgr plus cosine 60 is equal to 1/2. So this is just going to be 1/2 big mgr. So notice that the g's and the r's actually cancel. And we want to solve for little m. So little m is just going to be equal to, well, we have 2m minus 1/2 m, and that's just going to be 3/2 m. And that's going to be answer choice C. So that's a tricky one, but I think it's a good example. All right, now on to a classic. A bowling ball of mass m and radius r, whose moment of inertia through its center is given by 2/5 mr squared, rolls without slipping along a level surface at speed v. And we want to find the maximum vertical height it can roll to. So this is a very classic energy conservation problem. So what we have is we have some sort of object that's not just translating, but it's also spinning. So it's moving at a velocity v, but it's also rotating at a velocity omega. So what we have happening is two forms of kinetic energy are getting turned into gravitational potential. So we're going to find that mgh at the top is equal to the kinetic energy of translation plus the kinetic energy of rotation. So again, it's rolling, which means it has both types of kinetic energy. And we're given this in terms of v. So now we have to deal with evaluating each of these. So we're given that I is 2/5 mr squared. And then we also use the fact that rolling without slipping tells us that omega equals v over r. So again, if you ever see the word without slipping, that means that this relationship, this omega r equals v or a equals alpha r, anything like that, that means that these are probably used. So instead of omega, I'm going to write this as v squared over r squared. And notice the r's cancel. And then after cleaning up some things like canceling the mass from all the terms, we get GH equals 1/2 v squared plus 1/5 v squared. And then simplifying, we get GH is equal to, let's see, 1/2 is 5/10, and 1/5 is 2/10, so this is 7/10. So then dividing by dividing by g, and we do get the fact that h is equal to 7v squared over 10g, which is answer choice D. So notice that this definitely depends on the shape constant. So if this was a hoop or a disc or anything, not a sphere, it would go a different height. All right, next one. This is a very tricky one, even though it looks kind of simple. A solid cylinder rolls on the surface of an incline without slipping. Which diagram shows how the forces act when the cylinder is rolling down the incline? Without slipping. So it's rolling without slipping. So first, let's draw the forces we definitely know. So definitely, we have an mg force down. And we also are going to have a normal force acting directly out of the surface. I'm just going to put it right there, the point of contact. And then we have a friction force. So we want to find what way friction's going. So if it was a block sliding down the incline, so a block sliding down the incline, well, the block would be translating down, so the friction force would be up the ramp. So it is very tempting to just say, oh, it's going down the ramp, so friction goes up the ramp, so it's that choice. But here's where rolling actually makes a difference. So the bottom of the sphere is actually not moving at all. So that motion actually can't be used to figure it out. So we can actually see that, well, if you're rolling down the incline, well, your object is just going to rotate that way. So things don't just decide to rotate, there has to be a torque causing it. So the only way that happens if they're from the friction force is if there's a torque pointing to the right. So actually, friction in this case does in fact point up the incline, as opposed to just in this case. So that would be diagram 2. So it's for a different reason that the friction points up the incline. It's not just because it's moving down, friction goes up. So actually, even if it's rolling up the incline, it's still going to be up the incline. Friction is, at least. So very tricky, but this was the easier case. A hoop of mass m and radius r rolls at constant speed without slipping. What is the hoop's translational kinetic energy divided by its rotational kinetic energy? So let's just write what it wants. Translational kinetic energy divided by its rotational kinetic energy. So we want Ke from translation divided by Ke from rotation. So Ke from translation is equal to 1/2 mv squared, and Ke from rotation is equal to 1/2 I omega squared. And the fact that these are all numbers means everything should cancel somehow. So, once again, we have the magic words without slipping. So without slipping means that V is equal to omega R, or omega equals V over R. So I can replace my V with an omega squared R squared, because V is omega R. And then I have to deal with the bottom. So I want to remove this moment of inertia. So we're given that it's a hoop. And the fact that it's a hoop means that this whole thing is empty, except for all of the mass which is on the rim. So I is the sort of worst case scenario of mr squared. So the shape constant's 1. If it was a disk, it'd be 1/2, and you have that whole table and all that. But so the moment of inertia is mr squared, and I should at least be consistent with how I write it. And I have an omega squared. So actually, everything cancels. These two things are just identical. So it's actually just 1-to-1. So a hoop is the rare exception where its rotational kinetic energy is exactly the same as its translational kinetic energy when you're rolling without slipping. And also, little side note, this is actually always equal to the shape constant for your low moment of inertia. Now we got a lab question. A student performs a relationship to determine an experiment to find the relationship between the object's mass and its rotational inertia. So basically, we just keep changing the amount of mass that we're sticking on this whirligig apparatus, and we want to find how the rotational inertia changes. So as we're adding more mass, it appears that rotational inertia is increasing linearly. But we're asked, what does the intercept of the graph represent? So again, even though this is not a graph we've likely seen before, it doesn't change how we analyze it. So we're asked for the intercept, which means what happens when the independent variable is equal to 0. So the rotational inertia when m equals 0 is given by this point. So this is saying this point right here is the rotational inertia of the system if there is no extra mass attached. So anything that's not a rotational inertia is definitely wrong. So this is not a moment of inertia. 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 So it's actually just E. You just could have figured that out by looking at units. So again, the y-intercept has units of rotational inertia. So that's the only choice it could possibly be. But again, conceptually, you can think of this as the initial rotational inertia. So this is just how much inertia is in your system before you attach anything else. Which is why E is correct. Now on to some static equilibrium. Two blocks of masses m1 and m2 are connected by a massless string that passes over a wheel of mass m as shown. So the wheel has mass. So this also means it has a moment of inertia. So that's the big key to this problem. The pulley has mass. The string does not slip and exerts two different tension forces on each block and rotates clockwise. Which of the following statements about T1 and T2 is correct? Well, we can just go through. T1 equals T2 because the wheel has mass. No, that's true if it didn't. So if it didn't have mass, that's our first introduction to the Atwood machine. So before we analyze this problem by saying this had no mass, so we pretended it didn't exist. T1 equals T2 because both blocks have the same acceleration. Well, no, because both blocks have the same acceleration, that doesn't really have to do with the tensions. But I guess let's leave it, because that's not instantly being eliminated. T1 is greater than T2 because M1 is farther from the wheel than M2. Well, it doesn't matter how far the masses are, it matters where the torques are located. And they're both a distance of r away, so that's just false. T1 is greater than T2 because M1 accelerates upwards. Well, that's just false. We're given that we're not that doesn't tell us anything about why T1 has to be bigger than T2 because the values of the tension are definitely going to depend on the mass itself. And then T2 is greater than T1 because an unbalanced clockwise torque is needed to accelerate the wheel clockwise. This is definitely the simplest answer out of the bunch, and it's going to be the right one. So, again, tension points out from every point. So it is true that T2 acts up on M2, but T2 also acts down on the pulley right here. Similarly, T1 acts up on M1 right here, but T1 also acts down on the pulley right here. But since this pulley actually has mass, it's rotating. And it's rotating clockwise. So this must mean the torque pulling it clockwise is larger than the torque pulling it counterclockwise. So that's why it's simply E. And again, we can just eliminate B in hindsight because, well, the blocks having the same acceleration really doesn't relate to the fact to the tensions. And actually, just by looking at F net equals MA, you could see that if T1 equals T2, they wouldn't have the same acceleration unless if the masses were the same. All right, our first of many hoop and disc problems. A ring and a disk are shown above, and they have identical mass, radii, and velocities. How will the distances they move up the plane compare? So, anytime you're dealing with the hoop versus disk sort of thing, it's always looking at energy. So, we know that the height it reaches, mgh, is going to be equal to the total kinetic energy it has at the bottom. And we're given they move at the same speed. So, we have to remember there are two forms of kinetic energy because it's rolling without slipping. And we could even replace this omega uh, with a v over r if we wanted everything in terms of v. And now we just got to compare what's different. So the fact that they have the same linear speed means both for the hoop and the disk, this term's the same. So this one is the same for each. But then we have to look at the rotation term. So this is equal to 1/2 times I times v squared over r squared, which is equal to v squared over 2r squared times I, just to show what it actually depends on. So all this stuff is a constant. So we're basically just asking, how do the i's compare between them? Well, we have a hoop, which has moment of inertia mr squared, although we don't really need to know that. And then we have a disk, identical, that's just filled in, has moment of inertia 1/2 mr squared. So the hoop has a larger moment of inertia. So the hoop actually has more energy, meaning the hoop is going to make it higher. So it's all about the shape constant here. So this is different than the case where they're racing down the ramp. Because in this case, you're not starting with the same amount of energy. So you're basically saying which one has more energy at the bottom. Well, if they have the same translation kinetic energy, we have to compare how their rotational kinetic energies are going to compare. And the fact that the hoop has the same inertia, or sorry, has a greater inertia, means it must have taken more energy initially to spin that hoop up to speed because it's carrying all of its mass around far away from the center. So that's how we could have done this without even knowing the shape constant, is because moment of inertia is about how your mass is distributed. So the thing with its mass distributed farther away has a higher I. A wheel with rotational inertia I is fixed on a frictionless axle, and its angular speed is increased from 0 to omega f in a time interval t. What is the average power input to the wheel during this time interval? So we'll show two ways of doing this. So first, we'll do the definition of power. Power is equal to the work divided by the time. But due to the work energy theorem, we know that the work done on an object is nothing but the change in its kinetic energy. And the fact that it's just rotating means this is rotational kinetic energy. So we're just going to take the difference between its starting and ending kinetic energies. But this is actually starting from rest, so this term is 0. Meaning our answer is just I omega f squared over 2t. And that is answer choice B. Additionally, the way I solved this on my first attempt was using the fact that power is also equal to torque dotted with omega average. So the torque is equal to I alpha and omega average. And then we just kind of work everything out. So alpha is just change in omega over change in t. And I'll actually write it out, I guess. I'll write the full thing out. And average speed is just the average of the speeds. So I just add the two speeds. and divide by 2. But given the fact that omega naught is 0, we are just going to get the same answer of I omega f squared over 2t. I do like the work energy theorem way better. A uniform beam is hinged at one end and kept horizontal by a vertical cable. The tension in the cable is F. All right. So we're asked about the weight of the beam in the first part of this. So we can just draw our system here. So we have a cable, and we are given that that force is F. And we're also given that it's a uniform beam. So there is a weight force W exactly at the midpoint. And we're also given that there's a hinge right here. Given the fact we don't know anything about what's happening at the hinge, means that that should be the point where we're summing our torques around. So this distance right here, it's just going to be L over 2. And this distance down here is just going to be L. So this means that the torque caused by the weight has to equal the torque caused by the tension force. So the weight force, which is applied a distance L over 2 away, must be equal to the force F, which is located a distance of L away. And notice that L actually cancels out, so we get that W is just going to be equal to 2F, which in hindsight, we can see why this had to be the answer, just because the tension force is twice as far away, so it only needed to work half as hard as the weight. That's like the seesaw leverage problem. The vertical cable is now attached to the center of mass of the beam. What must the tension in the cable be? So the vertical cable is now attached at the center of mass. We want to find what the tension in the cable must be. So we already said that the weight of the cable was 2F in the new problem. So we're just going to set it up this way. So vertical cable is attached at the center of mass of the beam. So let's just draw that. So we got center of mass of the beam. Oh, that's not what I want. I want my arrow. So we have the weight force. And then we have the vertical cable attached at that same point. And we can probably tell that just by looking at this. And we don't know what this is, so we're just going to call this the new F. Well, they're at the same distance, and they're just opposites, so they have to be the same. So this means that these have to be equal to each other, because if not, there'd be a net torque. If the force of the cable was bigger, it would rotate counterclockwise, and if the weight was bigger, it'd rotate counterclockwise. So we can just see that F nu must just be equal to the weight. And we said that from the previous part, the weight of the beam is just going to be equal to 2 times the original F required. Or another way of thinking about this, which might be even the simpler answer, because this doesn't depend on knowing the previous part. If you're moving the cable halfway along the beam, if you're halving the distance, you have to double the force in order to get the same torque, just like the seesaw. So it's still a lever question. And I didn't change this number. This should say 15. A uniform ladder of weight W leans against, without slipping, a wall, making angle theta with the floor. there's friction between the ladder and the floor, but the friction between the ladder and the wall is negligible. Find the magnitude of the friction force exerted on the ladder. Okay, well, we're asked about the friction force. So if we just start labeling some things here, the ladder is going to have a weight force right down the middle. And then there's probably some weird contact force thing going on over there. And then there's also going to be some sort of friction force preventing the ladder from sliding, acting in some other direction. And we'll put that one down here. So given the fact that we know nothing about that force attached to the wall, tells us that that should probably be the point where we're summing our torques. So what we want in this case is we're just going to set that the sum of the torques is equal to 0 about the wall. And I might have drawn my friction the wrong way, but we'll deal with that. So the magnitude of the friction force exerted on the ladder by the floor. Well, we only have two things going on right here. We have the ladder, and we have the ladder's weight, and we have the friction. So we know those two have to balance. So we know the torque caused by mg has to be equal to the torque caused by friction. So first, we'll deal with the torque from mg. So once again, I think lever arm is probably the best way of doing this. Because anytime you have these sort of mg forces, they're purely vertical. So we're just asking, what is the shortest horizontal distance between the wall and the point where that force is acting? So I'm just going to draw my line of action right down the middle here. So what's the shortest horizontal distance? Well, in this case, I'm just asking what this is. Well, if this distance right here is L over 2, and my triangle angle is theta, well, that's just going to be the weight times cosine. So this is just L over 2 times cosine theta. Because again, if I redraw myself a little triangle up here, this will be L over 2 cosine theta. Goes up there. So that's a lever arm on that one. Because again, all the lever arm is saying is what is the shortest horizontal distance between these 2 points. So again, if that's theta, this is theta, so this is L over 2 cosine theta, because L over 2 is how far it is to the center of mass. So, this means that the torque caused by the weight is equal to the weight times lever arm, which is L over 2 cosine theta. And then we got to figure out the torque caused by friction. So friction, it's definitely going to be a horizontal force. So we can do the same thing, except now we can just deal with our lever arms in terms of the horizontal. Because again, we're going to have a friction force. We have a friction force that's going to act some way horizontally. I'll just draw my line of action like that. So our lever arm is just going to be the vertical distance. And that's just going to be L times sine theta. So the lever, so we have a force of friction F. We'll call it lowercase f for friction. And the lever arm is L sine theta. So friction force, after canceling the L, is just going to be 1/2 W times cosine theta over sine theta, which is cotangent. So we get W over 2 times cotangent theta. So this is a very hard one. If I were to rate this in terms of the multiple choice questions with torque, this is one of the hardest ones that I think I included. Because you got two different lever arm situations. A horizontal uniform board of weight 125 newtons and length 4 meters, supported by vertical chains at each end. So again, let's always just draw a picture. Horizontal uniform board. So uniform means arrayed in the center. We can put a weight force. And it's supported by vertical chains at each end. And there's a person of 500 newtons sitting on the board somewhere. We don't know where, so we'll just put them in a random spot. And they weigh 500 newtons. So we have, this is 250 newtons, the weight is 125 newtons, and the person weighs 500 newtons. What is the tension in the left chain? Well, don't overcomplicate this. The beam's at rest. So, we know that the sum of the forces must be 0. So this means that the 250 newtons up plus the other chain is equal to the two forces down. So, subtract 625 minus 250, and that's just going to be 375. So that's easier than it looked. This is a very weird looking one. A solid cylinder of mass m and radius r has a string wound around it. A person holding the string pulls it vertically upwards as shown, such that the cylinder is suspended in midair for a brief time interval, and its center of mass does not move. Center of mass does not move. The tension in the string is T, and we're given the moment of inertia. Calculate the linear acceleration of the person's hand. Well, I don't know anything about the hand, but what I do know is that the center of mass does not move. So I actually know that F net is equal to 0. So what does that mean? Well, it means that mg is equal to the tension force T. Because the center of mass does not move, so forces must balance. So, even though there is no net force, there must be a torque on the system, because, well, there's a tension force. So, the torque on the system is just going to be equal to the tension force, T, applied at a radius r away. But also, we know that tension is torque is equal to I alpha, and we know that tension is equal to mg. We said moment of inertia is 1/2 mr squared. And since there's no slipping, alpha is a over r. And after canceling the r's and multiplying by 2, we see that a is actually just equal to 2g. Because this r cancels with this r divides out with this r, and then the m's cancel out. So we get 2g. When a thin stick of mass m and length l is pivoted about one end, its moment of inertia is 1/3 ml squared. When the stick is pivoted about its midpoint, its moment of inertia is... If you just know the answer to this, good on you. You have a good memory. But we're just going to look at this. So anytime you're looking at two different moments of inertia, it's probably the parallel axis theorem at play. So what we're given is that mass m, length l. So we're given that moment of inertia about this point is 1/3 ml squared, and we want the I of the center of mass. Well, the formula we have relating moments of inertia is that I somewhere else is equal to I at the center of mass plus md squared, where d is the distance between the axes of rotation. So in our case, that's just a distance of L over 2. So this is saying that 1/3 ml squared, because that's our new moment of inertia, is equal to I at the center of mass plus m times L over 2 all squared. So we get 1/3 ml squared is equal to I at the center of mass plus 1/4 ml squared. So I of the center of mass, it's just going to be 1/3 minus 1/4 times ml squared, which is, as you may recall from in class, 1/12 ml squared. A 5 kilogram sphere is connected to a 10 kilogram sphere by a rigid rod of negligible mass. So this means we don't have to look at the rod itself for any of these. Which of the 5 lettered points represents the center of mass of the sphere-rod combination? Well, just by looking at it, the center of mass is a weighted average of where the mass is. So you can almost think of it as this is a 5, and then I have 2 5s stacked on top of each other over here. So it's definitely not E, because that's closer to the 5. It's definitely not D, that's closer to the 5. It's definitely not C, because that's in the middle. And it's definitely not all the way at A, because there's still mass at point E. So it's just B. But if you work it out mathematically, you will see that you'll find something consistent with point B. So if you do the formula for center of mass, you'd find that it's 1/15, because 1 over the total mass times, we have a 10 kilogram mass at 0 plus a 5 kilogram mass times a distance L away. So this would just be 1/3 L. And I definitely believe that this is 1/3 of the way along the rod. All right. And now we're asked another concept question. Which point should the axis of rotation pass for the moment of inertia of this system to be the greatest? So what we can remember is that moment of inertia is equal to a weighted average of distances squared times the individual mass values. So we know that I total for our system is just going to be the sum of each point mass times its distance squared from the axis of rotation. So we have to figure out where can we put the axis of rotation to make that number the largest. So first of all, just kind of looking at things, if we look at our parallel axis theorem, it's actually true that the moment of inertia is minimized at the center of mass. So we have this expression that I is equal to I at the center of mass plus md squared. So we can see that the moment of inertia depends on how far away you are from the center of mass. So really what we're asking is, what is the farthest point from the center of mass? Well, we already said this was like 1/3 of L, so we said this was the center of mass. So what point's the farthest from B? Well, that would be E. So it's just going to be choice E. And if you wanted to think about that a different way, if we pivot about point E, you are putting all the heavy 10 kilogram mass all the way at one end of the rod. So even though the contribution of the 5 kilogram is 0, the fact that the moment of inertia depends on distance squared means it's going to have a huge effect. The angular displacement theta of a rotating wheel is described by this equation. We're given theta, not A and B. What's the angular acceleration? So this is just calculus plug and chug. So we want angular acceleration, and we're given theta. So we know that alpha is equal to the second derivative of theta, because it's about acceleration, we have position. So one derivative, we get 2at minus 3bt squared. And two derivatives, we get 2a minus 6bt. That's choice C. Because again, this is omega and this is alpha. The uniform thin rod has mass m and length L. The moment of inertia through its center is 1/12 ml squared. So we're given that this is I equals 1/12 ml squared. We want to find the moment of inertia a point a quarter of the way from one end. So this is once again parallel axis theorem, because anytime you're asked about two moments of inertia, it's probably parallel axis theorem. So we're given the moment of inertia through the center of mass, and I will stop using the wrong arrow. So for parallel axis theorem, we just need one of these two moments of inertia and their separation. So we're given that this I through the center of mass is 1/12 ml squared, and we're given that this distance is just going to be, well, if this is L over 4 and this is the midpoint of the rod, so if this is L over 4, this must also be L over 4. So we know that I nu is equal to I through the center of mass plus md squared. So we just get 1/12 ml squared plus m times L over 4 squared, being careful with parentheses. So we're just going to get 1/12 plus 1/16 times ml squared. And let's see what that is. Well, oh boy. 12 and 16 with a common denominator. This is the point in the video where I get stumped and actually have to look at it. It actually turns out to be 7 over 48, which would not have been one of my guesses. So, because working out the fraction, 1/12 is 4/48, and 1/16 is 3/48. So you add them up and get 7 over 48, which remarkably is a choice. Each weight of a barbell is 50 kilograms, and the weights are 1.6 meters apart. The bar has negligible mass. What is the difference between the moments of inertia when the barbell is spun around its endpoint versus when it's shifted 0.1 meters to one side, as shown? All right, so we're just going to ask once again, just to look at the differences in the moment of inertias. So in this case, it's once again parallel axis theorem. So we know that I nu is equal to I through the center of mass plus md squared. So if we're just looking at the difference in the moment of inertia values, we're just going to subtract. So I nu minus I through the center of mass is just equal to md squared. So it turns out we don't care what these are individually. We just want to know what they're equal to when they're subtracted. So the total mass of the system is 50 plus 50 equals 100 kilograms, and their separation distance that the axis is moved by is 0.1. So it actually just shifts by 1. kilogram meter squared. And that's E. A ring and solid disk of equal mass and equal diameter begin to roll down the ramp. Which one wins? So, what's happening here is mgh is equal for both. But what's happening is the mgh is getting turned into kinetic energy of translation and kinetic energy of rotation. And once again, we're comparing here. So, well, we know that the moment of inertia is going to be bigger for the hoop. So, because more of the mass is farther away from the center. So this is larger for the hoop, which means that this is going to be smaller for the hoop. Because the two energies must always add up to the same thing, since the mgh is the same initial energy. So this means the hoop loses the race. So the disc reaches the bottom first. This is a classic. This is one that you should definitely catalog in your head, but be able to justify it. The rod in the figure shown is uniform and has mass m. What's the tension in the supporting string? Well, once again, I'm going to use my typical trend of figure out the point I don't care about and do the torques about there. So I definitely don't know what's going on at that hinge point. So I'm just going to sum all up my torques from that point. And we're given that there is a string going this way. And because the rod, of course, has mass, m, there's going to be a weight force right down the middle. So once again, we just balance torques. So we know that the torque caused by mg has to be the same as the torque caused by the tension. So once again, we're going to apply the lever arm definition of torque because we have vertical forces. So it works out nicely. So we're just asked, what is the shortest horizontal distance between the 2 points here? Well, here we can see that here's my lever arm for the weight force vector. So the shortest distance between these 2 points is just going to be, well, L over 2 sine theta. So the torque caused by mg is just the mg force times its lever arm of L over 2 sine theta. And then tension is actually going to be very close to just being identical. So we'll clear some of this stuff. So for the tension force, well, we just get a longer lever arm here. And notice it's the same. It's just that the distance is longer now. So if that's theta, this is also theta. Yeah, I drew my theta wrong. No, I didn't. I lied. So this is also just going to be L times sine theta. We have a tension force acting with a lever arm of sine theta. And sine theta actually cancels in this case. So tension is just going to be mg over 2. Interesting that even the trig function cancels this time. A penny farthing is a bicycle with a large front wheel and small back wheel. Suppose a person is riding a penny farthing on a flat roadway, as one does, covering the same distance in each unit of time. Same distance in each unit of time. Well, d over t. Well, that just means that v is constant. Which wheel has the greater linear speed and which has the greater angular speed? Well, the fact that the bicycle is moving at 1 unit is definitely telling us that the wheels have the same velocity. And now we just have to figure out how omega compares. So we know that v is equal to omega times r. So this means angular speed is equal to v divided by r. So the fact that the larger wheel has a larger radius means that its angular velocity has to proportionately shrink. So in this case, it is going to be d. Because the small wheel is going to be, it has less distance to travel to complete a revolution. So if every point on the tip of the wheel is moving the same speed, well, the smaller wheel has less distance to cover. So it's going to have a greater omega value. The diagram shows two disks of radius r and 3r fixed together to an axis. A mass m1 hangs from a string wrapped around the smaller disk, where m2 hangs from a string wrapped around the larger wheel. Which of the following values causes an equilibrium? Well, what we have here, so it's in equilibrium, so we know that the tensions have to be equal to the weight. So we know that the weight, the mg's are equal to the tensions. So we know that there's going to be a tension of m1g applied at the rim r, and there's going to be a tension of m2g applied at a radius of 3r. So we're just going to set the torques equal. So we know that the counterclockwise torque applied by the m1g at a distance of r has to be equal to the torque of the force m2g that's pulling it clockwise at a distance of 3r. So g cancels and even r cancels. So all we're given is that m1 has to be equal to 3 times m2. Because again, if you're tripling the radius, you only need a third of the force to get the same impact. So anything where m1 is going to be 3 times m2 will work. A gear containing 20 teeth on its circumference is meshed with a gear containing 60 teeth. If the angular speed of the 20-tooth gear is omega, what's the angular speed of the 60-tooth gear? Well, if these two gears are in contact with each other, this means that v is the same. So this means that omega r for the first gear is equal to omega r for the second gear. And you can think of teeth and radius as coming in the same ratio here. So we have omega 1 of the 20-tooth gear is equal to omega 2 times the 60 teeth. So you get omega 1 is equal to 3 times omega 2. So the small gear is moving 3 times as fast, meaning the large gear is moving 1/3 of the original speed. So that would be choice C. A rod at a horizontal tabletop is pivoted at one end. If we're applying a force at the other end to produce the same torque. We're just trying to figure out where can we place this force F to get the same effect as what's going on right now. Well, this is where lever arm is helpful, or we can also just see what is actually causing the torque here. I actually like the idea of perpendicular force here as our idea of what's causing the torque. So if I split my force here, I have two parts. This blue part is not doing anything. That's the parallel force component. But the thing actually creating the torque is going to be the perpendicular force component right here. And we can see that since this angle is also theta inside the triangle, this is just going to be F sine theta. So the torque is just going to be equal to F perpendicular times the distance, which is equal to F sine theta times L. So we just need to figure out where to place a force F to get this same torque. So this is T1. So next, we just want to generate the same torque by multiplying a force F at some distance r that we don't know. And if these two things are equal, we're just going to set f sine theta times L equal to f times r, and we get that r is equal to L sine theta, which is, interestingly enough, just the lever arm of the original force. A cylinder rotates with constant angular acceleration about a fixed axis. The cylinder's moment of inertia is 4 kilogram meters squared. At time t equals 0, the cylinder is at rest. At time t equals 2, its angular velocity is 1 radian per second. What's the kinetic energy of the cylinder at time t equals 2 seconds? Well, we're given its moment of inertia. We're given its angular velocity. It's just 1/2 I omega squared. One half times I times omega squared. Oh. And I plugged in the wrong value. So that's just going to be 2 joules. B. It's just plug and chug. A meter stick of negligible mass is placed on a fulcrum at the 60 centimeter mark. So that's 60 centimeters. With a 2 kilogram mass hung at the 0 meter mark. So there's a 2 kilogram mass hung from the 0. And there's a 1 kilogram mass hung from the 1 meter mark. The meter stick is released at rest in a horizontal position. Find the net torque. Well, we are given the meter stick has negligible mass, so we don't even need to include the fact that the center mass of the meter stick is applying a torque. We're just looking at the comparison in these two things. So the net torque, in this case, it's just going to be the torque caused by the 2 kilogram minus the torque caused by the 1 kilogram. And in our case, well, we're just going to look at our distances from the pivot. And realizing that we have our weight forces down here. So this is going to have a 20 Newton force, and this is going to be a 10 Newton force. So given that the fulcrum was placed at the 60, this is 0.6 meters. And given that this was placed at the 1, this is 0.4 meters. So we have a 20 Newton force placed at 0.6, and then we have a 10 Newton force placed 0.4 from the pivot. And working that out, we get 12 minus 4, which is 8 Newton meters of torque. A square piece of plywood on a horizontal tabletop is subjected to do horizontal forces. Where should a third force of magnitude 5 newtons be applied to put the piece of plywood into equilibrium? So, notice that this just means that the sum of the forces is equal to 0. So that's why it had to be 5. And also, we know that the sum of the torques need to equal 0. So first, let's notice what's going on here. So first, we need all of our forces to balance. So we need the 5 newtons to be going down. Because we have 10 newtons up, so we need 10 newtons down. So we know that the 5 newtons has to be down. And then we have to have the net torque be 0. So we have to make sure that it's going to balance the torque caused by this. So the easiest case where that's prevalent is just A. And again, C is incorrect because the force has to be down. E is incorrect because the force has to be down. B is incorrect because the force has to be down. Because we need the forces to balance first. And then for the torques, well, there's no torque generated from the force at D. But there is torque being generated on this corner by the 5, so you got to cancel it. A wheel of radius 0.5 meters rolls without slipping. It moves 20 meters in 5 seconds. Find the angular speed. Well, it says it's moving at constant speed, so v of the center of mass is just d over t, which is 20 meters over 5 seconds, which is 4 meters per second. So it's B. No, wrong. We want the angular speed. So we found the linear speed, but also remember that it is rolling without slipping. So rolling without slipping means that omega times r equals v. So omega equals v over r, which is 4 meters per second over 0.5 meters, which is going to be equal to 8 rads per second. All right. So next, compared to an object of the same mass and shape with a solid center, a hollow object's moment of inertia is always. So this is saying, how does the hollow case compare to the filled-in case with the same amount? So again, realize that I is roughly equal to a summation of mass times distance squared. So in the hollow case, much more of your mass is placed on the rim. So this is going to make your moment of inertia much higher. And again, just something to remember is the fact that the hoop has sort of the biggest moment of inertia of the main shapes because all of its mass is concentrated at the center. Whereas in the case like the disc or the solid sphere, the mass is evenly distributed, so a lot of it is close to the center of mass. A wheel starts from rest and has a constant angular acceleration of 3 rads per second squared. What angle does it rotate through? Well, we can just use the fact that delta theta is 1/2 at squared plus v0t. So we get 16 divided by 2 is 8 times 3 is 24 radians. And I am pretty sure I did this question before, but that's okay. Here it is again. If the following objects were rolled down an incline, which of the following would initially travel the slowest? So we can see that traveling the slowest is basically asking what A value is the lowest? Well, they're rolling without slipping, so we know that alpha is going to be equal to A over R, so alpha, A, same idea. But also, if they're rolling without slipping, we know that it's going to be caused by torque. So it's going to depend on moment of inertia, because alpha is equal to the torque divided by the moment of inertia. So we're just basically asking which object has the biggest moment of inertia. Well, it's not the solid sphere. Solid sphere has sort of the best moment of inertia. Center weighted disk, nope. And then end weighted disk or a hoop. Well, it's going to be the hoop because the hoop has literally all of its mass as far away from the rotation center as possible. The hoop always loses these race contests. But similarly, the hoop wins the how far can it go up the ramp contest, but it does lose the race down. A spherical marble of radius 3 centimeters rolls from rest with an angular acceleration of 4 radians per second squared. How long will it take for it to roll 100 revolutions? So again, we don't use revolutions. We use radians. So that's just going to be 200 pi. So we're just asking, how long does it take to go 200 pi rads. So we're just going to use the fact that delta theta is equal to 1/2 alpha times time squared plus an initial velocity term that's 0. So we're just solving 200 pi equals 1/2 times 4 times t squared. So 200 pi is just going to be equal to 2t squared, so t is square root of 100 pi. So that'd be answer choice B. All right, last two. A hoop of moment of inertia, mr squared. Rotates about its axis through its center perpendicular to the page, but also there's 2 point masses on it. What's the rotational inertia of the system? Well, moment of inertia is just going to be equal to the sum of all the moments of inertia. Or sorry, it's just going to be the sum of all the moments of inertia. So we have the hoop itself, which is mr squared. Then we have a point mass m, a distance r away, and we have another point mass m, a distance r away. And computing this, adding all these together, that's just going to be the total mass times r squared in this example. So that's just going to be, there's going to be 7 times 0.4 times 0.4, which is not a nice value. It's 1.12 kilogram meters squared. Three discs are glued together to make the pulley shown to the right. The radii of the discs are A, 2A, and 3A. And the masses M1 and M2 are both 1 kilogram. So this is 1 kilogram. This is also 1 kilogram. We want to find what M3 has to be. So we're given that this distance right here is A. This distance right here is 2A. And this distance right here is 3A. So we just got to set our torques equal to each other. So going clockwise, we have 2 torques. So we have M2 and M1's tensions are both pulling clockwise. And then we have M3 who's pulling counterclockwise. So we just know that the torque caused by M3 is equal to the torque caused by M2 plus the torque caused by M1. So for M3, that torque is M3G times the distance at which it acts, and that's in the inner pulley, so that's just going to be A. And then M1G acts on the farthest pulley, so that's actually going to be 3A. And then the M2G acts at the middle pulley, so that's 2A. So lots of things cancel. So G goes away, and the A goes away. So we get M3 equals 3M1 plus 2M2, which is going to be equal to 5 kilograms. And there you have it. 40 rotation multiple choice questions. I could not imagine you'd be asked anything significantly different than the main topics covered here. Again, blank problem set and solutions are in the description.